Welcome to our final episode of the virtual cosmic journey. Today we'll embark on the mission to discover, beyond the bright arms of stars, the cosmos where things actually get fascinating. You may assume the Milky Way could be the end of the universe, but guess what? It's much more intriguing and mysterious than your imagination. Let's consider the Milky Way galaxy as a bustling star city where stellar bodies take birth, live their lives, and die. But you know what? There's a full-fledged world beyond its brightening lights, usually regarded as the most lesser-known part of the galaxy. It's a dark, huge, quiet, and empty part of the Milky Way called halo. This dark halo zone is home to globular cluster bodies that seem like an ancient star club and have been around since the universe was young. They're like time capsules showing us what the early galaxy was like. Let's delve deeper into what's all the fuss about this mysterious dark halo. Certainly, it's not some stars, moons, or planets, but something very ghostly that never doesn't shine with any light but is known to have a powerful force of gravity. The space is all empty, dark, and distant from the Earth's crust. So what's the big deal with dark halo? That's the question scientists have been actively looking for. The dark halo could be the next normal part of the universe, but it's not. It's a fascinating sight that helps shape the galaxy, its formation, and how the Milky Way behaves. When space scientists studied the spinning of galaxies, they found something strange to ponder, and that's now famous as the dark halo. According to the statement of modern models of physical cosmology, the dark halo is a fundamental unit of the cosmological structure of the universe. It's an invisible, out-of-sight, non-luminous space that wraps up the entire galaxy in a hidden hug. Within the dark halo is the dark matter halo that isn't lit up like stars and moon, or you can consider it something like planets, but it's a completely different zone found around galaxies, including our own Milky Way. Somehow the halo is regarded as a hypothetical place that occurs from the decoupling of cosmic expansion and contains gravitational bound particles. The modern Lambda CDM model elaborates that dark matter halo or subhalos may have galaxies. It doesn't emit light, but it's strong, like a magnet, and pulls things with its invisible force, just like Earth's gravity pulls things down. However, we can't observe it with the naked eye, but it's very influential. It's like a strong friend who's always around, even if you can't see them. The dark halo has its own significance in studying the universe owing to its power that helps galaxies, including the Milky Way, come together and stay together. When galaxies spin, the dark halo ensures they don't tear or fly apart like a spinning top with its gravitational bound. Stars spin around the galaxies like a great grand ballet with a spinning motion called galactic rotation. If you can't assume the spin, just think of a galaxy as a giant merry-go-round and the stars as riders. The outer stars slow down when they move away from the center, but that's not the case with our galaxy. When the scientists observed the spinning motion, a plot twist was waiting to be uncovered. The stars weren't slowing down, instead they kept running around the galaxy at the same speed. It was unexpectedly fascinating, and it literally made the space community scratch their heads about the force maintaining the stars at the same rate as the first. After a thorough investigation, they came up with two theories. First, there's hidden motion in the galaxy, something they can't see, like a secret ingredient, which is dark matter. Second, our knowledge of relative motions needs to be completed. There is more chapter that should be uncovered. From radio waves as hydrogen gas, scientists implied every object to uncover the fuss about the same speed, but nothing proved fruitful. At last, a scientist named Ken Freeman came forward and studied the galaxy's unusual motion. He was sure there must be something extraordinary to help hold the galaxies together that we can't see. He named the force dark matter in 1970. It was the year when this hypothetical space got a title. Freeman thoroughly observed the expected decline in velocities was not present in NGC 300 or M33, and since then, scientists have been searching to see if dark matter is the missing piece of the puzzle. During the early formation of the galaxy, it was almost impossible to stick the sun, moons, and stars together owing to their hot surface. There was a force needed to merge these planetary objects gravitationally. Here, dark matter enters the scene as an early architect. The CDM was a special kind of matter that formed the framework in the early universe to hold. The universe had tiny bumps in density, almost like hills and valleys. Firstly, these bumps grow to a certain size, and then they stop expanding and collapse to form the basic building blocks, the dark matter halos. These halos kept on growing and even merged with other building blocks to form bigger ones. Inside them, you'll find tiny subhalos that create a sort of lumpy structure that we can't see directly, but we know they're there. The dark matter shows its magic there, as it's cold compared to the hot surfaces of baryonic matter, which allowed it to overcome the thermal pressures that kept the regular matter from collapsing. With the dark matter's gravity, the baryonic matter collapsed to form the first stars and galaxies. It's like a secret framework or a connecting dot that finally supports the galaxies to form, and without them, galaxies might not have found their shape in the early universe. With its great gravitational pull, the dark halo significantly impacts two special things: globular clusters and stellar streams. Let's first see how it influences the globular cluster. As we already discussed, this is an ancient club where old stars hang out together, but the dark matter halo has a say in where these star clubs go. Its gravity acts like a puppeteer that gently tugs the star clusters. When you look from a telescope, it seems like the stellar bodies following the cosmic strings of a dance. Later, the globular cluster's tug-of-war shape helps determine the star's path. Just like this, the dark halo also influences the stellar streams. Think of a river made of stars with a long trail that tells tales of galactic history. The dark halo also plays a role in the formation of these streams. Its gravitational pull creates ripples in space-time, which helps shape the streams, just like a sculptor shaping clay. Scientists use special instruments to study how globular clusters and stellar streams move differently than expected, and that's a clue that the dark halo is at work. With these studies, scientists can even discover how the structures move and interact, revealing their ultimate presence. The dark halo is pretty invisible to the naked eye, but since the day there was a fuss about a force that holds the galaxies together, the space community has been actively looking to find ways for its exploration. They've come up with clever ways to learn more about its path. First and foremost, they implemented gravitational lensing to map the path of dark matter with light distortion. When there's a lot of mass, like dark matter, it bends light that passes by it. This bending makes things behind the mass appear stretched or warped. Hence, if a galaxy is hiding dark matter, it will likely be exposed. Scientists also use the galaxy simulation method to explore the path of dark matter. These are super smart computer programs that create virtual universes on our screens. Scientists code everything they know about galaxies, like how stars form and how gravity works. They also program about the dark matter, since it plays a massive role in the formation, and then let the simulation run and watch how galaxies evolve over time. All these simulations help scientists observe if their theories match what they observe in real galaxies. However, despite the formation of the halo, there are massive arguments about its shape as well. The dark halo is flattened owing to the simulation of structure formation in a CDM universe, but most scientists argue that it's spherical, which is totally impossible considering the aspherical collapse of overdensities in the cosmic density field. The research on the invisible dark halos is still ongoing. The scientists aren't going to sit back and relax. They're like space explorers, using clever tricks and powerful computers to uncover their secrets. Since mapping the dark halo isn't just about knowing where it is, it's like solving puzzles that connect the universe's dots. So let's end the video here. I hope you have enjoyed our final take on the cosmic journey. Make sure to comment below on your experience and what you would like to see next.